Alrighty, y'all. Today we're taking a look at the rest of our Lab 13 final exam review. And this one we're doing Unit 2 with Kepler's laws, and also we're going on to all the light stuff we've been talking about, spectroscopy and whatnot. Alright, so the first thing we're looking at is Kepler's laws. Our first law says that planets orbit the sun in ellipses with the sun at one focus. Alright, so that says, well, a circle is a special type of ellipse without eccentricity. So the sun at the center of a circle is the sun at the focus of that special ellipse. Right? This is a much more eccentric ellipse. Right? Remember, eccentricity is just how much that ellipse is stretched, so how long it is. So a less eccentric ellipse would be closer to a circle, while a much more eccentric ellipse is much more stretched out. And in this case, I have the sun drawn close to one of the foci of the ellipse. Maybe it should be a little further out, but the point is being made that it's not this one, because this one just has the sun in the center when it should be further towards the outside. So we have that perihelion and aphelion that we've been talking about. So this one is bad according to Kepler's first law. Right? The second law of orbits is that the line connecting a planet to the sun sweeps out equal areas in equal times. Well, that's kind of easy to see with a circular orbit, right? It'll be moving at a constant speed the whole time. So all of my pie slices, if it's equal time, they'll have equal area. Now, it's a little harder to see with my ellipse. So if I go over to the orbit simulator real quick, right, I have not a super eccentric ellipse, but a little bit of an eccentric ellipse. And ignore the kind of artifacts all over it. That's just because I was hopping in and out of the tab, right? So we can see that as it's going around, it's going to go faster as it gets towards the perihelion when it's closer to the sun. And it's going slower out where it is right now, right? It speeds up and it goes slower out there towards the aphelion or aphelion, however you're supposed to pronounce it. The one that starts with an A, right? So it goes faster as it's closer to the sun. So if I come back over here, that means that in the same amount of time, so this will travel a further distance because it's going faster. It'll travel a longer distance along here when it's closer to the sun, right? So this pie slice, than when it's out here, it'll travel a much shorter distance like this, right? So this pie slice. Which kind of makes sense that in order to make them equal the same area, right? Because if I think of like this is kind of like a triangle, right? If I'm making it a much shorter triangle, it has to be, including all of this, right? It has to be much wider so that that triangle has the same area as a very skinny, very tall triangle, right? So obviously it's not triangles we saw as I was trying to draw that triangle. We ended up with a huge chunk missing. But that's the kind of idea that we're looking at. And again, we can use Kepler's second law to kind of look at Kepler's first law, where this one, it definitely isn't going to work, right? Because say it's, well, if it's going faster, closer, then maybe it has this much here, right? But if it's going at some kind of constant speed, I mean, there's a way to adjust the speed so that it's all the same area, but it's kind of weird because the distance from the sun is changing. I don't have one perihelion where it's close and one aphelion where it's further away, or aphelion. Right, so this one just causes a whole lot of problems and we just don't like it at all. So moral of the story is that this one's really bad and we don't like it. The third law of orbits, that the amount of time that a planet takes to travel around the sun, which is the period of the orbit, right, increases with the length of the long axis, right? And that's my perihelion distance plus my aphelion distance. So if I go back to my orbit simulator over here, I can see that, oh, you could I didn't know you could do that. That's kind of cool, actually. So anyways, ignoring that, I was just trying to scroll over. But we can see that my aphelion and perihelion distances, together it's about 1.8 AU, and I have a period of about 0.86 years. But if I hop on over to this one, Now my long axis is shorter. Instead of 1.8, it's about 1.1. And my period is 0.4. So I have a shorter long axis. So instead of my long axis decreased from 1.8 to 1.1, and my period decreased from 0.8 years to 0.4 years. So we see that in our orbit simulator, and that is also seen from the third long. So my period increases as my long axis also gets longer or increases. Okay. And now we can think about, using all of that, thinking about conservation of energy. How does my kinetic energy change during the orbit? Where is it the highest? Where is it the lowest? Well, my kinetic energy, that directly correlates with how fast I'm going, or my speed, right? So if my speed is higher, my kinetic energy is higher. So if I go back to my orbit simulator, which is, again, with all that artifacts because it's not liking me jumping in and out of the tabs, all right, we see it going much, much faster when it's closer to the sun at the perihelion than when it's much further away. All right, so it tells me on this side, my kinetic energy, or my speed's much higher, which means my kinetic energy is much higher at the perihelion. So we say Ke is at a max at the perihelion. How do you spell that? Perihelion. And it's at a minimum, all right? It's going the slowest at the aphelion. Right? So highest, lowest, max, min, right? How is my potential energy change during the orbit? Where's that highest and the lowest? Well, that just changes based on how far away from the planet I am. So a higher potential energy will be when I'm further away, and a lower potential energy will be when I'm closer. Right? So my potential energy max, that's at the aphelion, right? When I'm furthest away. And my minimum potential energy, that will be at the perihelion, or when I'm closest. Right? Now we think about, how is total energy, kinetic plus potential, how is that changing during the orbit? Well, I know my kinetic energy is increasing towards the perihelion and decreasing towards the aphelion. But my potential energy is doing the opposite, right? So my potential energy, so as I'm going this way, my kinetic energy is increasing, but my potential energy is decreasing. And I get here, and I get to a maximum kinetic, minimum potential. And then as I keep going, now my potential is increasing, but my kinetic is decreasing. And eventually I get here, and I'm at a minimum kinetic, maximum potential. Right? So if I'm adding them together and they're changing opposite like that, that shows us that energy is conserved, or it's not changing. My total energy, both of them together, is constant, which is the law of conservation of energy. Right? The energy can't come from anywhere. It just comes from kinetic energy turning into potential, and then the potential energy turning back into kinetic. Right? Moving right along. Law of gravity. All right? So, we have an astronaut who weighs 300 pounds on the surface of the Earth. And now we're thinking about, how much do they weigh on the surface of the moon? So, I always want to take this step by step. First thing I'm going to think about changing is the radius. So what happens when I change the radius? Well, I don't remember, so let's write down that equation. Equals big G times 1 and 2 over r squared, right? So my force from gravity, or my weight, is this gravitational constant times my mass times my other mass divided by the radius, or the distance between them, squared. So as I'm changing my radius, right, in this case, I'm going to be decreasing my radius. So as I'm going through this, I'm thinking of like, okay, if I have the Earth and I slowly morph it into the moon, how is that going to change the force of gravity on the person, on the astronaut? All right, so if I'm taking the Earth and I decrease its radius, I'm keeping the mass the same for right now. We're just thinking of it step by step. If I'm just decreasing the radius, I want to know what that's going to do to my force of gravity. All right? So I come up to my equation. If I'm decreasing my radius, right, I'm making this denominator smaller. So if I'm taking my whole number and making my denominator smaller, that's going to make my whole number bigger. Right? If I think about 1/4 versus 1/5, right? If I'm dividing by a larger number, that means I'll have a smaller part of the whole when I'm done. So if I'm decreasing my radius, I'll end up with a larger overall number. So I know that if I decrease the radius, or if I decrease the denominator, it's going to increase my force. All right, so I have my general trend, and I know I'm changing my radius by 1/4. All right, so let's take that 1/4. Well, I know for sure that my force of gravity is not going to be changing by 1/4. Because if I have 1/4 the gravity from 1/4 the radius, well, then that would be less gravity, but we just said it should be increasing, right? I also know it's not going to be a factor of 4 because I have this radius squared, right? That squared bit. So, well, let's just sort that out right away. So I'm going to take that 1/4, square it, right? And when I'm squaring a fraction, I can just square the numerator and then square the denominator, write them back together. 1 squared is just 1. 4 squared, or 4 times 4, that's just 16, right? So I've dealt with that squared part. That makes my life a little easier. But now I still have that problem where I can't just multiply this. I can't say it's just FG times 1/16, right? Because then that's decreasing my force, and we said it should be increasing. So what we're going to do is we're instead going to say, all right, well, my force of gravity on the Earth, I'm going to take that, and instead of dividing by 16, I'm going to multiply by 16. And that's going to be my new force of gravity. I'm going to call it on like that from change in the radius. All right, whatever it is. Either way, moral of the story is we're taking our force of gravity. If I were to just decrease the radius by 1/4, I'm going to end up with 16 times the gravity. Right? All right, so we got step 1. We figured out what the radius is doing. All right, well, what about the mass? All right, so come here and I have my mass. Well, I know I'm decreasing the mass, so let's come back to our system down here. If I'm decreasing my mass, I want to figure out what that's going to do to the force of gravity. So I come up here, and again, it doesn't matter which mass is which, right? We'll say that this one is the mass of the person, and this is either the mass of the moon or the mass of the Earth, whatever it is, all right? So if I'm taking this, well, the mass of the person isn't changing, the gravity constant's not changing. All right, so if I'm taking this mass and I'm decreasing it, right, well, that's just taking my numerator and decreasing it. So that's going to be decreasing my force of gravity. All right, so I come down here, and I know that decreasing my mass is going to decrease my force of gravity. All right, and we don't have that squared part to deal with like we did for the radius, so I can just take that mass, and I don't have to square it at all. I just can take it right as it is. So I'm having 1/96th the mass. Well, this works out really nicely because I don't have to square it. I don't have to square it at all. And also, right, if I took my force of gravity and multiplied by 196 or just divided by 96, that's decreasing it. That's doing exactly what I wanted it to do. So that tells me that if I'm decreasing the mass by 1/96, I'm going to take my force and it'll decrease by 96. All right. So I've talked about if I change the radius, and I've talked about if I change the mass, but what happens when I change both of them, right? Well, if I'm thinking about slowly morphing the Earth into the moon, right, the first thing I do is I shrink it down, and now that planet will have 16 times the force of gravity. But then I have this new planet that is the same size as the moon, but the mass of the Earth. And then I decrease the mass. Now from that new planet, I now have 1/96, the gravity of that new planet. Well, all that's getting really complicated. But what it all boils down to is I'm going to multiply their effects. Right? So the first thing I'm going to do, I'm going to take the force of gravity on the Earth. I'm going to multiply it by 16. Right? That's the force of gravity on that fake intermediate planet. But I'm also going to decrease it by 1/96. And that's going to give me the force of gravity on the moon. Okay? So it doesn't matter what order I'm multiplying these in, right? So I can just kind of smush them together like I can with fractions. So I'll have 16/96. And it looks like I have some common factors between the numerator and denominator. So I can simplify this fraction a little bit. I'm going to pull out 8 in the top, so that'll be 8 times 2 over, I think that's 8 times 12. All right, so my 8s will cancel. All right, well, 2 also, I can say it's 2 times 1 over 2 times 6, and my 2's will cancel, using 1/6. All right, so that tells me that the force of gravity on the moon is 1/6 the force of gravity on the Earth, which is a number that you may recognize. This is something we've talked about before, where I have that 1/6 factor is the result of increasing it by 16 times because my radius is smaller, but then also decreasing it by 96 times because my mass is smaller. So all of this put together is to say that if a person or if an astronaut, if she weighs 300 pounds on the surface of the Earth, well, on the surface of the moon, she's going to weigh 300 times 1/6, or 300 over 6 pounds. 300 divided by 6, that's going to be 50 pounds on the moon. All right? So that's how I get to my final answer for that one. Moving right along. Now we're looking at thermal radiation. All right? And we were going to draw a few different stars. So I'll draw the first one in blue. So we'll start A. It's the same size as the sun, but it's a little bit cooler. All right? So when I'm drawing stars and their emission spectra, the first thing that I want to be thinking about is the temperature, because the temperature is the easiest. All right? The temperature gives us directly the peak wavelength. So the peak wavelength is what tells me my temperature. That is directly true. A cooler star, right, well, that'll have a lower energy peak wavelength. The lower the energy, the longer the wavelength. So a colder star takes that peak and shifts it to the right. Right? But everything else held exactly constant. Right? So it'll shift my peak somewhere to the right. When the size is held constant, right? If I'm not changing the size at all, a colder star will have a lower intensity, right, than a hotter star. We can go see that if we look at our black body spectrum, right? As I decrease the temperature, I can see my peak wavelength shifting to the right, and my intensity is decreasing. Right? So this is what my star looks like if it's the same size as the sun, but cooler. Right? Now I want to be thinking about a temperature that's the same temperature. A star that is the same temperature as the sun, just a little smaller. Well, we were saying that temperature correlates directly with my peak wavelength. Right? So if it's a little bit smaller, it'll have a lower intensity. I can just do something like that. So now we've said that our peak wavelength correlates directly with temperature. So I'll write that off to the side. My peak wavelength, jump down here, that comes directly from the temperature of the star. But we've now seen that my intensity, or my maximum intensity of the star, that can come from two different things. It can come from the temperature, and it can also come from the size. Technically, it can also come from like how far away we are from the star, right? Much further away stars are going to look a lot dimmer, but we're going to assume for the most part that we're comparing things that we're looking at from the same distance, right? So I can get, from my peak wavelength, I can get my temperature immediately. But my intensity, I have to be a little bit more careful because my intensity will increase if I have a higher temperature and if I have a larger size. But if these are flip-flopped, right, a hotter one that's smaller, right, I don't know how my intensity might change. So that's why we have to be really careful to think about a cooler star should have a lower intensity, but only if the size is not changing. All right, so moving right along to my third one, we're going to be talking here about same size and temperature as the sun, but moving away. Well, if it's the same size and temperature as the sun, it's going to have the same emission curve as the sun. However, if it's moving away fast enough, we'll get redshift, right? Things that are moving away from us, those redshift, right? That's from the Doppler effect. So if I have that star I said was purple, I'm going to take this exact same curve and just shift it a little bit to the right. So same intensity. All right, that's not perfect, but it's the right kind of idea. All right, it's going to have the same intensity. It's not going to have the same peak wavelength anymore because it's moving away. All right, so those are my 3 stars, A, B, and C there. Looking at 2 more stars. Now we have star A and star B. I'm going to say star A. I'm going to call that. So I can color code things a little bit. And just so happens, when we're looking at what color each star would appear to the eye. Well, to the eye. I didn't mean to cross that out. I meant to underline it. To the eye means we're only looking in the visible range. So everything outside of this, I don't care about. I don't care what's going on outside of the visible range. I'm just looking at in here. All right, so star A, well, that is emitting much more blue light on this side than it is red light on this side. See, there's that huge difference. So star A, since it's emitting much more blue than red, star A is going to appear bluish, right? Which just so happens that I colored it blue. Wow, I wonder why I did that, or if I knew that was going to happen. Doing the same thing looking at star B, right? Star B is emitting much more light over on the red side than it is on the blue side. So star B would look much more reddish. Right? So we can see it's much higher in the red than it is in the blue. If we come back and look at the sun kind of peaks in the middle. So it's emitting roughly the same amount, right, of red and blue and everything in between. There's a little bit of a difference, but not enough to cause the difference in color. So the sun will appear whitish. We can look outside and see that. Again, star A and star B, we have a huge difference. For star B specifically, we have a huge difference between the amount of red light and the amount of blue light. And for star A as well, huge difference between the amount of blue light and the amount of red light. All right, so that's why they're going to appear different colors. All right, which one appears brighter to the eye? Again, we have that to the eye, which means we're looking in the visible range, right? And again, I can ignore everything else. We want to know which one would appear brighter. Well, that one will probably be star B. That one will be star B. So we can see it has a higher intensity for more of the visible range. So if I'm kind of thinking the area underneath this graph, it's much more than star A in the visible range. Right? So if I'm thinking just intensity, it's much more intense for more of the visible range. You can see that graph is just because the graph is above it. So the one that's brighter is going to be star B. And which star is hotter? Well, remember what we were talking about with the temperature. If I'm trying to figure out the temperature, the only thing I have to look at is the peak wavelength for each. So the peak wavelength for star A is in the ultraviolet, and the peak wavelength for star B is kind of in the infrared. It's like almost in the visible, actually, but call that in the infrared. Because star B has a peak wavelength that is shifted to the right, it's lower energy, it's a longer wavelength. Star B will be cooler, and star A will be hotter. So we'll say A is hotter, and B is cooler. Now it's asking which one's bigger. Well, this one's tricky, right? Because if I remember, size, well, that changes my intensity. But temperature also changes my intensity. But remember that a cooler star should be smaller. So if I took if I took star A and I tried to slowly turn it into star B. So if I took star A, kept it exactly the same size, and just decreased my temperature, it would shift over to the right, but its intensity would get smaller and smaller and smaller as it got cooler and cooler and cooler, because it's the same size. If I were to shift star A and turn it into the same temperature as star B, it might be somewhere down here with its intensity. In order to increase the intensity to what we're seeing from star B, well, I would have to increase the size. So star B, because it's cooler, it should be less intense, but the reason that it's not is because we increase that size and say that star B is going to be bigger. So which star is bigger? That'll be star B is bigger and A is smaller. Okay. All right, we're in the final stretch. We're just looking at a couple pages of spectroscopy now. All right, so our first question is asking about the spectrum of holdenium, and we want to draw the lines within the visible range. So if I'm talking about emission or absorption spectrum, I'm thinking about the transition between the energy levels. I don't care about the actual energy levels themselves. I only care about the transitions. So I'm going to write down every possible transition. Right? I like to think of these as levels in a building. So if I'm drawing my energy diagram, I have level, I'll write it on this side, level 1, level 2, level 3, and level 4. And remember, I don't want to get stuck in the elevator in between any of these levels. All right, so I can only move up in between the level, up and down in between the levels. All right, and I'll write down my EV on each. So this will be 5.3 EV. It's my energy of level 4. I have 4.7 EV. I have 2.5 and 0. All right. So if I am in my elevator and I am on floor 4, what buttons could I push to move in the elevator? Well, if I'm standing at the 4th floor and I push the button for the 4th floor, nothing's going to happen. And the elevator is just going to stay there, so that's kind of boring. So we can ignore that one, but we can go down to the 3rd floor, or we could go to the 2nd floor, or we can go all the way down to the 1st floor. Okay. Well, then, what if I'm on the 3rd floor? Then if I'm on the 3rd floor, well, I could go up to the 4th floor, right? But that's the same as just going down to the 3rd floor. It's just backwards. So we'll skip that one, and we'll say, okay, I can go down to the 2nd, or I can go down to the 1st floor. All right? And then if I'm on the 2nd floor, again, I can go up to the 4th, but I already have that one here. I could go up to the 3rd, but I already have that one here. Or I could go down to the 1st. This is every possible transition I could make. Right? And remember, what I've drawn is emission, right? I have to, when I lose that energy by emitting a photon, it'll go down in an energy level. But it's the same exact lines if I wanted to go up, right? If I absorbed a photon, it would go up to the higher energy level. So that's why whenever I was on the lower levels and I was like, well, I've already accounted for this because it's the same as going up or down. All right. So now we just need to figure out the numbers associated with all of this. So like I said, I could go 4 to 3. I could go 4 to 2. I could go 4 to 1. I could also go 3 to 2 and 3 to 1, and then I could go 2 to 1. Those are all of my possible transitions. Well, 4 to 3, so I'm going to take my level 4 energy and subtract my level 3 energy, and I'm going to do the math in my head. So it'll be 5.3 eV minus 4.7, and that'll be 0.6 eV. Okay. Then going from 4 down to 2, right, that'll be 5.3 minus 2.5. That'll be 2.8 eV. Again, I'm trying to do all the math in my head. Sorry if I get anything wrong. I don't think I did thus far, but I'll check my work as I go. And then going from 4 all the way down to 1, well, that'll be 5.3 minus 0. So that'll be 5.3 eV. Transition there. All right, moving on. Now we're at level 3, going down to level 2. So that'll be 3 minus 2, so 4.7 minus 2.5. And that will be 2.2 eV. Yep, that'll be 2.2 eV. And then going from 3 to 1, I go 4.7 down to 0. So it'll be 4.7 minus 0. That'll be 4.7 eV. Now lastly, going from 2 to 1, going 2.5 to 0. So it'll be 2.5 minus 0, 2.5 eV. All right. So I have all of my energy transitions. Now I have to think about, well, I'm only drawing the ones that are in the visible range. I have to think about which ones those are. All right, so I'm going to go through and figure out what's in the visible range. So the visible range, it looks like it's ending at 1.55. All right, so anything less than 1.55, that's going to be our infrared cutoff. We'll say anything bigger than 3.5 is going to be our ultraviolet cutoff. All right, anything bigger than 3.5 is going to be ultraviolet. There are more precise numbers for that, but just for this diagram's sake, that's what we're going to say. So if I have 0.6 eV, well, that's lower energy than 1.5, so that is not visible. That's going to be infrared, right? If I have 2.8 eV, well, that's on my diagram, 2.8, right around here. So it's going to be this kind of like a bluish color for that. There's my 2.8 eV. That's going to be visible. We got that one. Okay. 5.3 eV. Well, that one is much higher than our visible range. So that one's going to be ultraviolet. Maybe if I could write, I'm trying to make my U's and my V's not look like the same letters. Sorry. All right. Moving on, we have that 2.2 EV. Well, that one's also right in the middle of my range. So I'm going to have this kind of yellowish green color in here. All right. This one matched a lot better than this one did, but that's okay. All right, so that's that one there. 4.7. That one again is going to be too high. It's going to be off my chart. So that one's also too high energy, so it's above higher energy than my visible range, so that's ultraviolet. And lastly, 2.5. Well, using process of elimination, this is my last transition left, and I've only found 2 of the 3 lines that I'm looking for in the visible spectrum. So 2.5 is definitely going to be visible, which we can also see because it's right here. I'm going to use this kind of bluish color for this one. It's kind of in that blue-green range. So I can check mark that. All right, so I found my 3 visible lines. If I were to use this element with this emission spectrum and I was going to make a fluorescent lamp out of it. All right, so that was the kind in Holden in the observatory. When we looked at the lights in the ceiling, we saw the lines just like the discharge tubes. Well, what we saw, it's asking what we would see it as. What we saw was bright lines on a dark background. And the way I like to think about that, I can circle bright lines on a dark background. That's what it's going to be. The way I like to think about that is we are not going to see light unless it's coming from somewhere, right? So I have these bright lines because Holdenium can emit that light, right? So that light has a source. We found where it's coming from. These 3 bright lines are coming from the Holdenium because it can emit only those wavelengths of light. And the rest is going to be dark because there's nothing else producing light. The bright rainbow background, right? If I had a rainbow background, something has to be producing that light. But Holdenium can't produce light. It can't emit light that's not these 3 wavelengths. So it can't give us that bright rainbow background that we would be expecting. So it has to be bright lines on a dark background because the only source of light can only emit those 3 lines. Now, conversely, if we're observing the spectrum of a star that has Holdenium in it, well, I kind of spoiled this a little bit because I said it was the other one. I said conversely, so those would be the dark lines on the bright rainbow background. Because now we have the star, right? Star is emitting thermal radiation. Things that are hot, that emit light because they're hot, those emit that continuous spectrum, that bright rainbow background. So that, now I have that bright rainbow background because I have a source for it. It's coming from the star, right? And the Holdenium in the outer layer, well, the light's being emitted from the star. So I draw my star here. Light's being emitted from the star. It's emitting all of the light. But what's happening is in the outer layer, right? We'll say the atmosphere is here-ish, right? In the atmosphere, what's happening is Holdenium is absorbing the 3 specific wavelengths, right? It's now absorbing, so it's going up in its energy levels. It's now absorbing them, so now as it's passing through the atmosphere, only some of the wavelengths are making it through. So it's absorbing here. It's absorbing, we'll say it's absorbing this one here and this one and this one, right? It's absorbing the different wavelengths, so the rest of them get through. So my bright continuous spectrum, most of it's getting through, but those 3 specific wavelengths aren't getting through. They're being absorbed, so they end up leaving these kind of dark patches where we don't have any light at that wavelength. Moving on with Holdenium. All right, we're on our last page. We've almost made it. All right. These look very much like the spectral lines that we just saw for Holdenium. All right, we had 2.8, 2.5, and 2. So that was our 2.8, 2.5, and 2.2. You can see, though, that they're shifted a little bit over. But they aren't quite in the right place. Exactly, they're shifted a little bit to the right. And we said before that when things are moving away from us, they get redshifted. So we said that. I can say if things move away from us, that's redshift. If things are moving towards us, that's blue shift. Right? So we saw that I had 2.8, 2.5, and 2.2. These lines look like they're shifted to the right. They're shifted towards the red. They're shifted towards infrared. That is redshift. So what direction is it moving? Right away. Because it's redshifted, I can say it's moving away from us. Okay. If I wanted to conclude something about the velocity of the star, well, right off the bat, I'd have to say it's moving pretty fast, right? Because I don't see redshift if a car is driving down the road. It's not going to look a different color if it's moving away from you than if it's moving towards you. So the velocity has to be moving pretty fast. And we can figure out how fast it's moving if we remember that equation that we used, right? Our change in the wavelength is my original wavelength. My change in my wavelength divided by my original wavelength, we'll call that wavelength 1, equals my velocity divided by the speed of light. The c is the speed of light. All right, where that change in wavelength, that delta lambda, you can write that as my lambda 2, or what I'm observing, minus lambda 1, and again over lambda 1, v over c. So what I could do is I can look at this, I can estimate, all right, well, 2.8, the wavelength is about 445. So wavelength 1 is I should write that, lambda 1, 445 nanometers. All right. And my new wavelength that it's shifted to looks to be about 455. I say lambda 2, 455 nanometers. Again, I'm just kind of eyeballing it and guesstimating. And the speed of light, that's that c, that's 3 times 10 to the 8 meters per second. All right. So if I plug in all my numbers, all right, it's going to be 455 minus 445 divided by 445 is v divided by 3 times 10 to the 8. And I solve for this velocity. All right, so I'm going to multiply my 3 times 10 to the 8 to the other side. I'm going to end up with 455, minus 445 over 445 times 3 times 10 to the 8. That's going to be my velocity. If I were to punch that into a calculator, that would tell me my velocity is 6.7 times 10 to the 6th meters per second, which is very fast. All right, if I want to put that, that's 6.7 times 10 to the 3rd kilometers per second. If you've ever run a 5K, this is 7 kilometers per second. This is much faster. So if you ever run a 5K, that's your 5 kilometers. It's going much, 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 much further than that in a second. All right. So what direction is it moving? It is moving away from us. Velocity, very, very fast. All right. So just being able to roughly approximate it, it's shifted a little bit, so we'll have some velocity. All right. We observe another star with Holdenium as well, and now we want to compare its motion to that of the first star. Well, again, I have my 2.8, my 2.8, my 2.5, and my 2.2. Now we can see each of them is shifted much, much further than they were up here, where they just shifted a little bit, right? So if it's shifted further, that means it's moving much faster. All right. It's moving a lot faster. If its velocity is a lot faster, that means its shift is going to be a lot bigger as well. All right. So we can, if we wanted to, we could do the math, figure out how fast it's going based off of the shift, but we're just going to say it's going a lot faster. All right. And then, yep, congratulations. You're done with your Astro 101 labs. I hope you enjoyed your labs. And I also hope that you found this video at least a little bit helpful. Let me know if you have any more questions about this or anything else that you want me to try to explain, and I'll do my best to try to explain it, because I guess Sydney explains stuff.